Good morning. Welcome to Environmental Geology. We'll be presenting a lecture for the next hour on climate and the greenhouse effect. We'll be focusing in on atmosphere and winds, ocean circulation, what is climate, and what is the greenhouse effect. Have to start out with the atmosphere. The atmosphere is comprised mainly of nitrogen, which is inert, and oxygen, which is 21% of the atmosphere, and then trace gases, which include argon, and the next on the list is carbon dioxide. In the worksheet that we do in class, or online in this case, we look at what 280 parts per million means. That is a concentration of carbon dioxide in the atmosphere in 1850. It is changing, and some people say, well, it's a trace gas, because we'll see it's a very important trace gas. Many of these figures are derived from the book, which is why I chose them for this lecture. It just shows, again, that nitrogen is the dominant component, and oxygen, number 2. Argon, number 3, is an odorless, non-toxic, non-reactive gas. But there are other greenhouse gases other than carbon dioxide. Water vapor, methane, CH4, and carbon dioxide. These gases help keep the Earth from being unbearably cold. The atmosphere has a distinct structure to it. We live in the troposphere, which is the lower part of the atmosphere. The temperatures decrease as you go up in the troposphere. The stratosphere, the temperatures increase. And the difference between the troposphere and the stratosphere is called the tropopause. And this is an area where basically you would know if you ever flown in an aircraft. Most weather takes place in the troposphere. The stratosphere is less influenced by weather. Okay. We're not going to worry too much about the upper part of the atmosphere. It's thinner and thinner. Most of the atmosphere is contained actually within the troposphere and the stratosphere. The troposphere varies from about 7 kilometers or 4 miles near the poles to about 17 kilometers near the equator. In other words, 8 miles high. And again, that's where planes tend to fly because there's the least amount of turbulence there. The temperature in the troposphere is related to the heating of the Earth by solar radiation. We call that insolation, which means incoming solar radiation. The SOL, of course, stands for Sol is the name of our sun. This is not like insulation, which you put in your wall, which has a U in it. It's just different. So as we said before, temperatures decrease going up in the troposphere and then increase going up in the stratosphere. Within the stratosphere, there is an ozone layer. Ozone is a variety of oxygen, which is O3. Ozone in the stratosphere helps protect us from ultraviolet radiation. The ozone layer is about 15 kilometers or 9 miles up. And basically, the ozone layer screens out harmful ultraviolet radiation. One of the things about ozone in the lower atmosphere, it's not good. It's what creates smog. And on a smoggy day, there's a lot of ozone in the air, and it's hazardous to breathe. But in the stratosphere, it protects us, again, from ultraviolet radiations, which cause sunburn and cancer. So we're going to have a couple clicker questions here. So which of the following is incorrect? You just use your clicker if it's A, B, C, or D. We live in the troposphere. B, Everest touches the stratosphere. Most weather occurs in the stratosphere. Or the troposphere is 7 to 17 kilometers thick. So I have to click on response system. Hang on a second. Everybody click in? So everybody got C. Most weather occurs in the stratosphere. Try this one. Which of the following is correct? Temperature decreases in the troposphere and the stratosphere. Temperature decreases in the troposphere and increases in the stratosphere. The Earth's atmosphere is 80% oxygen and 20% nitrogen. And D, ozone is concentrated in the troposphere. Click in. And the answer is B. Temperatures decrease in the troposphere and increase in the stratosphere. These clicker questions are here to give us a selection for the midterm exam questions. You may see these again on the midterm. So the Earth has a radiation budget, which determines the surface temperature of the Earth. The amount of incoming solar radiation, or insolation, has to be balanced by the amount that's going out into space. 30% of the incoming solar radiation is actually reflected by the Earth back into space. This is called albedo. Albedo means reflectivity. So ice has a very high albedo, reflects back much of the energy. Clean ice, 90%, as we will see. Now, much of the radiation is absorbed by land and re-radiated back to space. Some of the is absorbed directly by the atmosphere, and this is where greenhouse gases are particularly important. The energy from incoming solar radiation is redistributed by the atmosphere. More energy comes in at the poles, as the equator, and less energy at the poles. So we can see this energy balance, the heat surplus at the equator and the heat deficit at the poles. This drives global winds on the planet that redistribute the heat. The tropical heating drives what's called a Hadley circulation cell, with rising winds at the equator and descending winds at about 30 degrees north and south latitude. These rising winds, as the water vapor and the air rise, it gets colder and it will tend, therefore, to rain out. So it rains like heck at the equator, what we call the meteorological equator. When air descends, it is a high pressure system. High pressure systems are dry. So the areas around 30 degrees north and 30 degrees south are dry. Can anybody tell me what's found around 30 degrees north and 30 degrees south? The Sahara, the Kalahari, the Altiplano, the Great Australian Desert, and the Great Sonoran Desert of the US. Deserts, right? These are areas which are dry. That's what this figure shows, that precipitation versus evaporation. If it's green, there's more precipitation over evaporation. If it's yellow, there's more evaporation than precipitation. So the Mediterranean region, as you know, if you've seen pictures of Greece or Italy, is quite dry. So again, the rising of the air and would normally go all the way to the poles, but it's broken into two larger cells, which we just saw here. A cell here, and then there's another cell here at the pole. So again, as air rises, the temperature of the air decreases by about 5 degrees Celsius per kilometer, or about 9 degrees Fahrenheit. This is called the adiabatic lapse rate. Cold air holds less water, thus it rains heavily in the tropics, where there are rainforests. Should also note that low pressure systems usually have rain associated with them. And in a low pressure system in the northern hemisphere, air flows counterclockwise around it. On a high pressure system in the northern hemisphere, air flows clockwise. This is in part driven by what we call the Coriolis effect. The Earth's rotation causes moving air and water masses, or other things moving at planetary scale like missiles, to be deflected to the right in the northern hemisphere. So if we shot a missile from the North Pole, we shot it toward Denver, it would be deflected to the west or to the right in the northern hemisphere. If we fired a missile from Los Angeles to the east toward New York, it would be deflected to the right. There is a very good movie on the Coriolis effect called the Coriolis movie. Please watch that on the eCollege site. So again, the Coriolis effect helps control planetary winds. So these are those cells of rising air and falling air, basically falling air and rising air. There's actually a low pressure generally centered on the poles also. This drives winds. So the winds associated with this rising Hadley cell here are from the northeast. These are called the trade winds. South of the equator, the trade winds are from the southeast. So it's the northeast trades and the southeast trades. Where they come together, it's called the intertropical convergence zone. And this is basically the meteorological equator. To the north, we have the descending Hadley cell generates these deserts. And the prevailing winds that we see in this region are from the west, and they're called the westerlies. This is just a pretty picture illustrating all of these various effects, the general high here and the general low at the meteorological equator, which is called the intertropical convergence zone. So that's what drives winds on the planets. What about the oceans and the ocean currents? So the oceans, the typical temperature in the tropics, if we go to places where these live, everybody recognize what that is? A coral. So corals live in the tropics to a certain extent, slightly outside the tropics. The tropics are defined by temperatures of about 28 degrees Celsius. So if we go to Jamaica today, okay, Jamaica in the summer, it gets warmer during the day, but on average, the ocean temperature stays at about 28 degrees Celsius. That's about 80 degrees Fahrenheit. If we go to Jamaica in January, the ocean temperature is about 28 degrees Celsius. It's a great thermostat, like the thermostat on the wall that keeps the temperature, a constant temperature in the, at the equator. The subtropics, Bermuda sits about here, marks a subtropical temperature. If you've ever been to Bermuda in the winter, the water's a little chilly. It's 18 degrees Celsius. It's about 64 degrees Fahrenheit. Now you can go swimming, but it's a little chilly. And that marks the subtropics. And that's the northern limit of reef growth. You don't get reef growth north of the Bahamas. If we go into the deep sea, the temperatures are cold. All the water in the deep sea is derived from the areas near Antarctica and the areas between Greenland and Europe, the so-called Norwegian Greenland Sea. The cold water, the temperatures here are below freezing on land. In the wintertime, it gets near freezing, and it forms cold deep water that moves out into the deep sea and moves out into the deep sea. So in effect, you can almost describe temperatures on Earth by these three temperatures. The currents help redistribute heat. So if we look here, we have a wind coming from the west here and a wind coming from the east here, the trade winds and the westerlies. They drive these circular gyres of currents. This is the Gulf Stream North Atlantic Canary Current System centered on Bermuda. There's a great gyre like this in the Pacific, coming from the Kuroshio Current of Japan down to the California Current and then into the North Equatorial Current. One in the southern Atlantic, one in the Indian Ocean, and one in the South Pacific. These currents redistribute heat. One of the most important and unusual features of surface currents is that this so-called Gulf Stream North Atlantic Current System has an extension to the north called the North Atlantic Current, which delivers heat and warm water to these high polar latitudes here in the area basically near Scandinavia and Greenland. What that does is this North Atlantic current is delivering heat to this region. This is a map of heat loss of the oceans. Another way you can think of this is these purple colors, the ocean's losing a lot of heat. What does that heat do? It warms the land. So one of the things we often say is what keeps Europe warmer than North America is this delivery of this warm water on the Gulf Stream North Atlantic Current System. If you look at England, let's say Scotland, we go to Edinburgh, Scotland, right there. And if we look due west of it, we're in Labrador. And I can tell you it's much chillier in the summer in Labrador than it is in England. This statement that this delivery of warm water is what keeps Europe warm is not 100% correct because the atmosphere is also very important in delivering heat to this area. If you cool water in this area, it becomes more dense. It becomes more dense and it mixes. It mixes down to over 1,000 meters and forms a very dense water mass that flows out called the North Atlantic Current. This is a deep current, flowing typically around 3,000 or 4,000 meters in the deep sea. This is the surface current. This deep current flows into the Southern Ocean here and begins to come up toward the surface in the Pacific in what we call upwelling. There's actually a continuation of the return flow in the surface. This has been dubbed by Wally Broecker of Lamont Doherty the Great Conveyor Belt. Why this is important is you will hear, and there was some discussion, we may be affecting the conveyor belt, putting fresh water in, say by melting Greenland's ice sheet. If we put fresh water into the surface of the oceans, it means it's less dense, which means we could be affecting the strength of this conveyor belt. If the conveyor belt weakens, what happens to the surface temperatures in Europe? They go down. So there was a discussion that global warming could cause cooling in Europe. And to a certain extent, there may be somewhat true, but from our understanding right now, it will not be much of a cooling in Europe. So we're going to try a couple more clicker questions now on reviewing these principles of how the atmosphere circulates and how the ocean circulates. So first question, the prevailing winds in New Jersey are A, from the west, B, from the north, C, from the east, D, from the south, and E, from above. And you said, half of you said, ooh, there we go. Winds in New Jersey are from the west. Yes, they are the westerlies. We are under the influence of the westerlies in New Jersey. If Dr. No, James Bond fame, launched a missile from his base in Jamaica toward New York City, it would be A, deflected to the west or to the left, B, deflected south, C, deflected north, D, deflected east, or E, deflected up. Click in now. And it is D, deflected east, to the right in the northern hemisphere. So we look from Jamaica toward the North Pole. To the right is to the east. Climate question 3. Air circulates around a low pressure in New Jersey, a low now, A, clockwise, B, counterclockwise, C, ask Mr. G, he's the weatherman on News 11. D, it depends on the direction it came from, and E, you can't tell. Click in now. Hang on. Click in one more time, sorry. And the answer is B, counterclockwise around lows, clockwise around highs. The questions will be posted with the PowerPoint so you can review your answers later. The average ocean temperatures around Jamaica, winter, spring, summer, or fall, sounds like a song title, are A, 28 degrees Celsius, B, 18, C, 14, D, 2, E, it depends on the season. And it is 28 degrees C, or Celsius. The temperatures at the bottom of the oceans are 28 degrees Celsius, 18 degrees Celsius, 4 degrees Celsius, 2 degrees Celsius, or E, depends on the season. It's actually 2 more or less correct answers here. 2 is the correct answer. It actually depends where you are on the bottom. There's some places it's as warm as 4, but this is close enough. All right, So what's weather? Well, weather, the atmosphere and the oceans govern physical conditions called weather. I had to look up this definition. You understand what weather is. You're dressed a certain way because of the weather, okay? It's the temperature, pressure, moisture content, humidity, wind, cloud, just all the stuff Mr. G will tell you about for the weather forecast, right? It's a short period of time. It's a great saying in Colorado. You like the weather? Wait 10 minutes, okay? Because it can change in 10 minutes. Or it may stay the same for a heat wave, 3 or 4 days. But it's on a minute, from minutes to hours to days. So what's climate? It's the average weather for a particular region and period, typically a 30-year average. So basically what you're wearing today is determined by the weather, but what you have in your closet is determined by the climate. The clothes you have in your closet, if we were living in Florida, you would not have a winter coat in your closet because it's a different climate. And that's the difference between climate and weather. Will you need that winter coat in January? Yes. Could there be a day when the weather in January is 72 degrees Fahrenheit? Absolutely. It happened a couple years ago. So there is a difference between weather and climate. Global climate are persistent weather patterns that exist for about 30 years on the various criteria that we just talked about. Temperature, pressure. So how long do you have to average? Well, that's a good question. 30 years is usually cited. Now this is a good example. These are temperatures going from 1980 to about 2007. And as you can see, these are average global temperatures, and they bounce around. This is called interannual climate variability. The warmest year on record in certain compilations was the 1998 El Nino record, and this particular one, the 2005, sticks out. But you can see that if you put an average through, the average is all up. Now let's say you try to average for a shorter period of time. In this case, 8 years was chosen. The trends are all over the place. So this is important when we answer the question, for example, we'll come back in the next lecture, has global warming stopped? This looks really scientific. It's like back in chemistry lab. We put the Bunsen burner on, we heat the water. Heat the water measures temperature through time. You may have done this in high school. And then you measure the temperature after you get it to a given temperature level, how long it takes to decay away. The response time is the amount of time it takes to get about halfway toward equilibrium. What's equilibrium in a flask like this? Well, it's 100 degrees Celsius, right? Boiling point. Doesn't get warmer than that. So the time it takes to heat this up to halfway to boiling point is called a response time. The response time of the atmosphere, okay, is on the order of hours, certainly days. Okay, if we're in Jamaica, it's 10 o'clock in the morning. It's 80 degrees Celsius. That sun gets to zenith, it gets to the top, and it's beating down. What happens? The temperature rises, and it's getting to equivalent 80 degrees Fahrenheit, excuse me. It's 28 degrees Celsius. It'll shoot up to the high 90s, that is to say low 30s in Celsius. What happens? Around between early afternoon, clouds form, and it rains like heck, and it cools down. That's a tropical thermostat, but it also illustrates the idea the atmosphere responds very quickly. What's the warmest days in the ocean at the Jersey Shore? If you want to go get the warmest temperature, when would you go? January? June? June 21st? No. Nobody's gone to the Jersey Shore? Okay. It's usually the first week in September. Okay. The oceans have a response time, which is a couple months. Okay. Arctic sea ice, we'll talk about that. The minimum in Arctic sea ice is in mid-September. This response time is longer. So the oceans have response times on days to months. I should mention land surface. Land surface coming back is very rapid. As we come out, what's the hottest time of the day? On a hot summer day, the sun's out. What's the hottest time of the day? It's not noon. about 3 o'clock. The response time of the land heating up is about 2 to 3 hours, okay, to reach equilibrium. Sea ice, as I said before, is basically on the order of several weeks. Now, the great glaciers on Earth, there's glaciers in the mountains we call mountain glaciers, and there's glaciers that are ice sheets, and we'll come back to that, cover Antarctica. Their response time of a mountain glacier is on the order of decades to 100 years. For the big ice sheets, it's anywhere from hundreds to thousands of years. Okay, so, and finally the deep ocean. We talked about the temperature in deep ocean being 2 degrees Celsius. How long does it take to turn over that deep ocean? And the answer is anywhere from on the order of 1,000 years. So here's a clicker question for fun. In terms of climate, okay, what is the coldest day of the year in New Jersey? December 21st to 22nd, which is what? Solstice, right? It's the shortest day of the year. That's when the insolation, on average, is minimum, the amount of incoming solar radiation. B, December 25th. C, Groundhog Day. D, it's impossible to tell. And E, January 5th. 25th, sorry. And you all guessed about right. Okay. By the way, is it the 25th, or is it the 20th, or is it the 31st, or the 1st of? It's getting close to. It's in that period of time, late January. We all know it didn't work out this year, right? The hottest day of the year is today, give or take a few days. 20th to about the 30th. That period of time of July is the hottest. But the weather's not showing it, but the climate does. And that illustrates the difference between weather and climate. All right, here's another clicker question. This is testing your common sense ahead of the actual question. Why do most people go to the shore in summer? A, to see Snooki and Seaside. B, psychologists have shown that the rhythm of the waves is soothing. C, because the high heat capacity, and by the way, those could be true, because the high heat capacity and thermal inertia of the oceans keep it cool. D, to wager the house in AC. And E, to get vitamins from the sun. Click in. We only have 3. I got 5 clickers out. Let's go. There we go. And it's said in a scientific fashion, so it's kind of like, intimidating. Because the high heat capacity and thermal inertia of the oceans keeps it cool. That's a way to say something that you knew ahead of time, that it's cooler at the beach than it is in New Brunswick, right? On a hot day, today's probably going to reach 90. But if it's going to be what? Cooler at the shore, quote unquote. And the reason why that is true, again, is large land masses heat and cool quickly. They have extreme seasonal temperatures reached about a month after solstice. Upper oceans heat slowly, with extreme temperatures reached about 2 months after solstice. And that's what this graph shows, that the temperature changes on land are much larger and they basically follow the forcing, that is the change in the incoming solar radiation, much more closely. This one lags. And the concept of leads and lags in the climate system is very important. So there are these things called feedbacks, that we have an initial change. We warm the planet. What happens when you warm the planet? You increase evaporation, right? If it's a hotter day, you're going to evaporate more water out of a pond or an ocean or a puddle in your yard than if it's a cloudy, cool day. Common sense, right? So more water vapor goes into the atmosphere. If you increase the amount of water vapor, what do you do to the atmosphere? You make it trap more heat. What happens when you trap more heat? You make it warmer. And this cycle continues. This is a positive feedback loop. We have to introduce the concept again of albedo, which is a fancy word of saying reflectivity. The Earth averages on the whole a 30% albedo. That is to say, it reflects back 30% of the sun's radiation. On fresh snow or ice that's not dirty, you're reflecting back about 60 to 90% of the sun's radiation. If you're looking at water, water's absorbing 90% of the radiations, only reflecting back 10, maybe 5%. If you go out to a golf course, well, if you go out to blacktop, okay, that material is just absorbing heat as much as water, if not more. But you think, oh, I'll get away from it in a nice grassy golf course or a nice grassy park. Grasslands basically absorb a lot of heat too. Not as much as that blacktop, not as much as the water, but they still absorb a lot of heat. Bare soils absorb less heat. They reflect back more. So this sets up what's called an albedo temperature feedback, which is another one of these positive feedbacks. Okay. So we think about the Arctic, and the next slide will tell you to watch a feedback from the Arctic from Vice President Gore from the movie An Inconvenient Truth. But let's say we have the Arctic Ocean covered with sea ice. What's it doing to the incoming solar radiation? It's reflecting back 90%. Okay. What happens as we start to melt that ice? By the mid-century, we may be ice-free in September in the Arctic. Not year-round, but what happens then? We've replaced that ice with water, and the water's absorbing more energy. And so you would have a warming causing melting of ice, which cause this further warming. In this slide, we talk about the initial change being a cooling, which increases snow and ice. If you increase snow and ice, you get higher reflectivity, less solar radiation is absorbed, and you go to greater cooling. Again, that's a positive feedback, whether it be due, if we could, again, replace this with global climate warming, warming would decrease snow and ice. It would mean more solar radiation and therefore greater warming. Does that make sense to everybody, this particular one? This is called albedo feedback. And again, Vice President Gore does a very good job of explaining this and the Arctic. And we'll come back to the Arctic in the second lecture. There are also negative feedbacks from low clouds. So if we're in the tropics, we already talked about this. We're in Jamaica, clear morning. What happens as we begin to evaporate much more? We form low clouds, and those low clouds rain out like crazy. Okay, that ends up as a negative feedback because what you have is increased evaporation, more low clouds, okay, basically decreases the temperatures, decreases evaporation, and the whole process serves as a thermostat. That negative feedback offsets the warming, okay, that's occurring in Jamaica. So the temperatures tend to stay at a constant temperature. Now, positive feedback does occur from clouds too. What's a colder winter night? One with clouds or one without clouds? If it's a cold and starry night, you have no clouds. And the Earth radiates its radiation into the atmosphere and into space. If you have high clouds, it acts as a blanket, okay? And basically, high clouds will give you a positive feedback. High clouds, so incoming radiation generates evaporation, precipitation that goes into high clouds, which tend to trap more heat. We'll talk about the effects of carbon dioxide on the atmosphere in the next lecture. But in order to understand how these work, you have to understand what these feedbacks are and how they can potentially work. So let's go to another clicker question. And the question is, what is incorrect about albedo? A is how reflective a surface is. B averages 30% for the Earth. C averages 60% for snow and ice. I give the answer here. I'm sorry, the slide got messed up. And E is controlled by CO2. And the point of this slide, I won't bother with the clicker. We'll see. I guess you all got it right. Yes. The carbon dioxide is not a feedback by itself. But carbon dioxide will trap more heat. Trapping more heat causes more evaporation. And more evaporation goes into some positive feedbacks. All right. Another clicker question. What is incorrect about clouds? A, they provide a positive feedback mechanism. B, they provide a negative feedback mechanism. C, are a major unknown in our understanding of the Earth's climate system. D, warm and cool slower than the ocean. And E, will increase on a warmer planet. So what's incorrect here? And it's all over the board. So let's go through this. The answer is D. Clouds do provide a positive feedback mechanism if they're high. If they're low clouds, like in Jamaica at 2 o'clock in the afternoon, they provide a negative feedback mechanism. They are a major unknown in the climate system. These are all true. And they will increase on a warmer planet. Another clicker question. So climate is changing all the time, and humans cannot change it. B is a long-term, 30-year average of temperature, precipitation, and other effects. C is the same as weather. D is changing when we get one bad winter of snow. And E is tropical in New Jersey. And A is certainly wrong. Climate does change all the time. That's a true statement. I will not argue that. But we have the capability of changing weather and climate. We can change our climate. Do you think that tearing down forests changes climate in a region? There's a good example. We can have a discussion about whether or not you think CO2 being released by humans is changing climate. But certainly, putting macadam, that is, say, asphalt, all over Manhattan Island has changed the climate. The average temperature in New York is different than it was when the Dutch lived there. That's a fact. Okay? We have changed climate. We have changed that climate locally. We can change global climate too. So if we're one example, without CO2, we're releasing soot, right? So that soot gets into the atmosphere, ends up all over the place. But some of it ends up on ice. So do you think that a Greenland ice sheet, which has clear ice on it, clean, or a Greenland ice sheet that has sooty ice on it, which is going to melt faster? The sooty ice. And this is actually a concern that people have been tracking this most recently. That Greenland is in fact melting faster in part because not just CO2 warming, but also due to other effects. And that brings up what else we're doing to the atmosphere. This is Mount Pinatubo, it's the largest eruption in my lifetime, 1991. In Mount Pinatubo, so in the 20th century, we'll revisit that temperature has gone up by about a degree, 1 degree Celsius on average. Okay. In 1 year, 1993, temperatures globally decreased by ½ degree Celsius. The explosion of Mount Pinatubo released dust, but more importantly, sulfate aerosols. Now, aerosols are, aerosols. Okay. That's not what we mean. By aerosols, well, your hairspray is an aerosol. It's a fine solid particle or liquid droplets in a gas. Sulfate, often done as SOx, sulfur oxide, whether or not it's SO2, SO, SO3. So it's written SOX, sounds kind of cool, SOx. Right? Pollutants are often SOx and NOx, nitrogen and sulfates. The sulfur dioxide, whether it comes from volcanoes or your tailpipe, tends to cool. By the way, the cleaning up of the atmosphere with catalytic converters This is an environmental geology class, right? That actually has released much less sulfur dioxide. The burning of dirty coal, though, releases more. So carbon dioxide warms, sulfur dioxide cools. Carbon dioxide warms, SOx and dust cool. This is dust over Bangladesh. Here's India. This is dust. Dust tends to cool. Okay. So that's another component of the climate system. But it brings us to the greenhouse gases and the greenhouse effect. So the contribution of the main greenhouse gases are water vapor, carbon dioxide, methane, whether it be from cow farts or methane released from marshes, ozone, nitrous dioxide, which our dentists used to use, so-called laughing gas, and chlorofluorocarbons. Chlorofluorocarbons are CFCs. Okay. What CFCs are used in the old style deodorants, okay, and in refrigerants. The Montreal Protocols ban the use of CFCs. Can anybody tell me why CFCs are bad other than their greenhouse effect? The ozone hole that opened up in Antarctica told us about the depletion of stratospheric ozone, not the stuff in the troposphere. That's bad, remember? If you go to LA or even New York on a day like tomorrow, you're going to look out and see in the distance this smog and ugh. A lot of that basically is due to ozone. But ozone in the stratosphere protects us. But ozone is broken down by CFCs. So whoever answers that we can't affect the planet's atmosphere and its climate is dead wrong, because with the Montreal Protocols, Jim, check what year that was. I think it was 1980s, 1986. We banned the use of CFCs. And as a result, the ozone hole in Antarctica is beginning to heal. We can change the atmosphere. So come back to carbon dioxide, a greenhouse gas. It was 280 parts per million in 1850. Today, we'll see this in the next lecture, it's 401 today, in this month, parts per million. We've released over 110 parts per million by fossil fuel burning and land use changes. Now, somebody will say, but professor, water vapor is a much more important greenhouse gas. Yes, well, we'll come back to that. That is true. But let's see how the greenhouse gases work. It's not directly analogous to a greenhouse, but basically, like a greenhouse, trapping heat, the greenhouse molecules basically absorb solar radiation and radiate it back. And some of that acts like a blanket. So in the video from Vice President Gore, he will talk about how release of carbon dioxide, and he calls it pollution. We could have that discussion. Carbon dioxide is a pollutant under the President Obama's administration of the Environmental Protection Agency, and of course under the later President Bush, under his EPA, it was not a pollutant. Okay, so it's a political statement there. But the release of carbon dioxide has thickened the atmosphere. So the amount of incoming solar radiation, take this number as just a relative number. It's in what's a watt per meter squared? It's a measure of how much energy is coming in. So coming into the atmosphere is about 343 watts per meter squared. The natural greenhouse effect means that we basically are trapping about 150 watts per meter squared. Okay? What that means, by the way, is that in the absence of carbon dioxide, well, wait, somebody tell me what you think the average temperature of the Earth is today. On average, whether it goes from the frosty poles to the tropical thermostat of 28 degrees Celsius. So what's the average? What's the average between 28 and 0? 14? So the average is about 14. It's actually about 15. Okay? Everybody with that? Celsius? Does that kind of make sense? Sometimes numbers, we throw numbers at you as scientists. The numbers are important sometimes because if they tell you something about the process. Knowing that the American Revolution was in 1776 tells us something about the rates of change of society since then. Okay? What if it had been 1466? Well, things would have happened a lot slower, right? So it tells you about the rates of things. So this warming that we talked about in the 20th century, we will see this average surface temperature of the Earth in 2014 is about 15.8 degrees Celsius. The 20th century is about 15. Let's say there was no CO2 in the atmosphere. None. And we'll come back to this. Mars is an example. The surface temperature of the Earth will be minus 18 degrees. But professor, how do you know that? We'll come back to that with the Stefan-Boltzmann equation. But the enhanced greenhouse effect, so this slide is probably a couple years old. This is probably when there was about 380 parts per million in the atmosphere. It's about 2.7 watts per meter squared. That is the so-called greenhouse warming. How does this work again? All right, so the sun emits its radiation as a wavelength. Okay, so that wavelength is peaked in visible light, which is good. That means you can see me, because light is the way our eyes evolved to see. What did they evolve to see? The Earth radiates radiation back, not in the form of light, but in the form of infrared radiation. And so it's a longer wavelength. So if we looked at the Earth from space, we see reflected light, but we don't see the heat. If we evolved on another planet where we could see radiation in this frequency or this wavelength, we would be able to see that heat. And in fact, satellites can see that heat because we designed their eyes to see in that wavelength. What's shown here are absorption spectra for carbon dioxide, ozone, and the total water vapors here. What it shows is if this is the radiation going out from the Earth, this is where CO2 is absorbing energy. Another way to look at it, if we had those eyes that could see heat, this room would be blurry. That makes sense? In other words, CO2 is absorbing that radiation. Once again, the Earth's energy balance is determined by incoming solar radiation versus emitted radiation. And the Earth's balance between those two fluxes or energies. I put this up. I don't expect you, unless you're interested in physics, to really go back to this equation. But what this equation does is simply say, with symbols, what I said before. The incoming solar radiation is equivalent to what's going out. And it's proportional to a constant and temperature to the fourth power. If you solve that equation for the Earth, what its temperature would be in space without CO2, this is where that minus 18 degrees Celsius comes from. This is basically the Earth, the difference between a snowball planet with an average temperature of minus 18 degrees versus the planet we know and love of 15 degrees is due to carbon dioxide. So I encourage you to look at the movie Vice President Gore Explains the Greenhouse Effect. In detail, the greenhouse effect and a greenhouse are similar in that they both basically trap heat. But the greenhouse itself works primarily by preventing absorbed heat from leaving the structure. The greenhouse effect on Earth is because the gases absorb outgoing energy and reemit some of it back to the Earth. And the story is that we live on a Goldilocks planet. We go to Mars. Mars is too cold. Now, Mars is twice the distance of the Earth, twice the distance from the sun as the Earth. Okay, it's 2 astronomical units. But that's not why Mars is cold. 4 billion years ago, liquid water flowed on Mars, and the components of life probably existed. And in fact, life may still exist in primitive form on Mars. But Mars lost its atmosphere. One of the reasons why the Earth's atmosphere has not been lost is we have a very strong magnetic field, which helps trap the atmosphere. Mars, 4 billion years ago, its inner, we didn't talk about inner cores and all that too much, but there was a little bit of that in the book. The outer core solidified. The outer core is the source of the magnetic field, and Mars lost its magnetic field and lost its atmosphere. What about Venus? It's half the distance to the sun of the Earth, but basically its temperature is incredibly high. Its temperature is many, many, many times Earth's. 460 degrees Celsius at the surface, many times hotter than the pizza oven. And the reason why is not because of its position in space, but because its atmosphere is 90% denser than the Earth, and it consists of 96% carbon dioxide. Because of that, in the Goldie House world, Venus is too hot and the Earth is just right. So let's take a 5-minute break. That is the end of the very first lecture.